Welcome back to Statistical Reasoning. We are finishing up Chapter 8 today, the Hypothesis Testing chapter. Today we'll be working on testing a claim about a mean. And I will go over the three different methods of doing it. I'll go over the p-value method, the critical value method, and the confidence interval method, though I would suggest you use the p-value method as we move forward. So today we're going to be doing a mean versus a proportion when we're testing, and we're doing a single one. So some of the symbols that we have to make sure that we are using. So our sample size is still n. Our sample mean is x bar. Our sample standard deviation is s. And our sample population mean is mu of x bar. So mean for the population. We have some requirements like we do with every test that we run. Our sample has to be a simple random sample. And in this case, it either has to be normally distributed, so it has to semi-fit the bell curve, or, so not an and, it can be normally distributed, or we would like our sample size to be greater than 30 subjects. If one of those fits, then we don't have to worry about the other one. When we're going through this, you could do it by hand if you want to find your t-score, or we can use technology, which I will mostly focus on, and I have uploaded videos on how to do that with your calculators. So if you want to find the t-score, you would find x bar, you would subtract the mean of the population, divide it by the standard deviation of the sample, which is then divided by the square root of n. When we're doing a t-score, you have to make sure you use the t-distribution table, which is table A3. You have to use the degrees of freedom, remember, which is n minus 1, so 1 less than your sample size. And you would do that with both the critical value method and the p-value method. So our requirements of normality, or n is greater than 30. If the original population is not normal, then go ahead and look for their sample size being larger than 30. If that's good to go, we're moving forward. If your sample size happens to be less than 30 but still more than 15, and if you look at the normality, it's fairly close, go ahead and still run the t-test. For the rest of it, you really shouldn't run anything that is less than 15 and it's not normal, but for the sake of this textbook and the practicing, we will go ahead and do it even if it doesn't fit the criteria. So some of the properties of our t-distribution. The student t-distribution is different for different sample sizes. Need to learn to write smaller. The student t-distribution has the same general bell shape as a standard normal curve, but it is wider and it reflects greater variability, which is then, that means it affects its standard deviation. It does have a mean of t equals 0. Because I just said our standard deviation is going to be affected, our standard deviation with the sample size is greater than 1. As your sample size gets larger, the student distribution gets closer to normal. So those are just some of the qualities. Okay, so the scenario that we're going to work with is looking at how much sleep adults get. So the National Health and Nutrition Examination Study looked at some people and recorded how much sleep they got per night. Notice there's not a ton there. There's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We only have 12, which is cited at n equals 12. So one of the things we're going to have to do is check for normality, which I'm getting ahead of myself. Let's look at our checklist. So is our sample a simple random sample? As far as we know it is, so we're going to check that one off. Now, is it normal or is it greater than 30? Well, definitely 12 is not greater than 30, so we do need to check to see if it is normally distributed or close to that. So to do that, you either need to do a histogram or you need to do a normal quantile plot, and I have uploaded how to do a histogram so that you can make sure you get that done. So looking at this, it does look fairly normal. It's not great because we have a little bit here, but it's not bad either. If this was a little bit less, then we'd be even better. But if you're looking at this normal quantile plot, it actually doesn't look bad, right? We've got most of the information is here in the center with a little bit on the outside. So it looks pretty normal. Remember, it doesn't have to be perfect. So we're going to go ahead and work through it. So first, let's think about what the claim is. So the claim that was being stated, that the mean amount of sleep for adults is less than 7 hours. So if I write that in symbols, our claim, now notice it says mean, so we have to use mu, is less than 7 hours. So then we'll go ahead and write our hypotheses. Our null, remember, is always equal to, so mu is equal to 7 hours. And so the claim is actually the alternative. Mu is less than 7 hours. In the statement, when you were reading it up above, it said to use a 0.05 significance level. So our alpha is 0.05. So now we're going to go ahead and run the test. So I'm going to run a t-test. And again, I have put that video on Blackboard so you could run it. I do not know anything about the standard deviation of the population. That is why it is a t-test and not a z-test. This is unknown. If I run that test, I get a t-value of negative 0.290, so that's my t-score, which then gives me a p-value of 0.3887. I'm going to go ahead and compare my p-value to my alpha level, 0.3887 compared to 0.05. My p-value is definitely greater. Since my p-value is greater, I am going to fail to reject the null. So how do I write that statement? So as I look at this, my claim was not with the equality, it was with the other one. And I did not reject the null, so therefore there is not sufficient evidence. And make sure you can write this final statement. There is not sufficient evidence to support the claim that the mean amount of sleep for adults is less than 7 hours. Okay, so now we're going to go ahead and look at the critical value method. And remember, they are the same reliability, so we should end up with the same answer. So let's see if that happens. So we start by looking at the claim. The claim has not changed. The claim is still that adults get less than 7 hours. So mu is less than 7 hours. My hypothesis has not changed. Mu is equal to 7 hours. and mu is less than 7 hours. They still had an alpha level of 0.05. Now, when I think about this, because this is a less than, if I think about it on a distribution curve, less than is only one side, and this is less than down over here. So this is a one-sided, so this 0.05 is all within this tail. So when I do a alpha of 0.05 with a one-sided or a one-tailed, all of the significance is in that single tail. Well, what that means then is that because these are symmetric, that there is a significance over here of also 0.05. So when I'm looking at what my confidence level is, I do not want to write that yet. I have 0.05 on this end, I have 0.05 on the upper end, so I have a total of 0.10. So then 1 minus 0.10 gives me a 0.90 confidence, or a 90% confidence level. And that's what I'm going to have to use when I'm working with my critical value. So now remember that I have an n equals 12. I have 12 in my sample size. When I'm finding the test for the critical value method, I have to do a degrees of freedom. So that is 12 minus 1, or 11. So I have a degrees of freedom of 11. That's important. And I'm doing a 90% confidence level. Or I could just think of it as a 0.05 in a one tail. Okay, so I am going to go ahead, I did put the chart on here to look at. So let's go ahead and think. So we have area in one tail or area in two tails. Since we started with area in one tail, I'll go ahead and do that. So I had 5% in a single tail. So here's 5% in a single tail. So I'm going to use this column. And then I had a degrees of freedom of 11, so I'm going to go find that. So I'm here. So where they intersect, that is my critical value. So 1.796. So if I look at what this is saying, is my critical value is 1.796. In the test statistic, I got a negative 0.29. My test statistic for my problem that we're working on with the adult sleep is not within the critical area. It is not less than my critical value. Since it is not less than that, then I have to fail to reject the null, and therefore I have the exact same results as I had up above. So again, that's good because we know they should give us the same method, and it did. Okay, now I could use a confidence interval method, which remember is not going to necessarily always give us the same amount or the same results. So it's a good way to estimate what's happening. So let's go ahead and do that. When I'm doing this, remember the whole beginning part is the same. You still state your claim. My claim was that the population mean is less than 7 hours for the amount of sleep. My null is still mu equals 7 hours. My alternative is that mu is less than 7 hours. Still have an alpha of 0.05. So this is important that I work with just like I did on the critical value method. The 0.05 is just over here because it is just left-tailed with it being less than, but it is symmetric. So if I have 0.05 over here, I really do also have 0.05 on the upper end. So to figure out what confidence interval I'm using or confidence level, I have 5% on both ends, so I have two of them. So I have 0.10 for my significance, so I'm going to do 1 minus that, which is 0.90. So I will be finding a 90% confidence interval. So we did do, and I have a video attached back in section 7.2 on how to find confidence intervals on the calculator. So if you need to review that, go back to section 7.2 and click on that video. If I go ahead and do this in my technology, I get a confidence interval of 5.80 is less than mu, which is less than 7.87. Now, our claim, which is less than 7 hours, is within that interval. So I can't reject the null since the 7 hours that I'm focused on is within there. So I failed to reject the null. And so in this case, my confidence interval method gave me the exact same answer as my other two. It was just as reliable in this case. Let's look at one more scenario. We have the mean body temperature is 98.6. So we had some data collected. They came up with 106 subjects. Their mean was 98.2 degrees Fahrenheit. The standard deviation was 0.62 degrees Fahrenheit. We're using an alpha level of 0.05, and they want to test the common belief that the population mean is 98.6 degrees Fahrenheit. And you probably heard that for years. I know I have. So first we'll look at our requirements. Is it a simple random sample? As far as we know it is. Does our population, is it normally distributed, or is n greater than 30? Well, we have an n of 106, so our n is definitely greater than 30, so I'm not going to worry about this. I don't need to draw a histogram or a normal quantile plot to see if it is, because I have met one of the requirements and it is an OR, so I'm good to go. So on this one, I'm just going to do the p-value method to check for the test. So we have to start with our claim. That's really bad, so let me try that again. Okay, so our claim was that the mean body temperature is 98.6 degrees Fahrenheit. Now because our null is always the equality, our claim in this case is the null, which is opposite of the example we did above. Now, because they're just focused on is it equal to 98.6, I don't care if the alternative is greater than or less than, it just has to be different. Since it just has to be different, we're going with an alternative of mu is not equal to 98.6 degrees Fahrenheit. They told us to use an alpha level of 0.05. I don't know anything about the standard deviation for the population, so again I'm going to run a t-test. Going to plug our information into our technology. I'm going to get a t of negative 6.61. Now that gives me a p-value that is very small, and when I look on the calculator it looks like it's 0, like it's not possible, but what's happened is it's been rounded. So there's a 1 somewhere way out there, I just don't know where. So what we do is we call it a 0 plus, which means it's almost impossible but not quite. It's just really, really, really small. So now I'm going to compare my p-value to my alpha level. So this is really, really small. This is 0.05. Well, my p-value is definitely less than 0.05, so I am going to reject the null. And so if I look at my options, this time I have the equality within my claim, and I am rejecting the null. So the statement is, there is sufficient evidence to warrant rejection of the common belief, which is the claim, that the population mean is 98.6. I'm going to abbreviate a little bit here to make it fit on the paper. Okay, so that's how you're going to run through that. Now, if by chance you happen to know the standard deviation for the population, the only difference is you are going to run a z-test. So if you know this, you're going to run a z-test, which what that does is it changes your statistic. It is now z equals x bar minus mu of x. Since you know it, you're going to use the standard deviation for the population, and you would divide by square root of n. So the only difference is this right here. It went from being S to sigma, or the standard deviation for the population, and in your technology, instead of doing a t-test, you would run a z-test. Okay, so with that, that ends this section, and that ends chapter 8. Go ahead and look through all the examples, look through your assignments. If you need any questions, please let me know. Have a good day.